Let's take a look at a couple more examples of improper integrals. For example 5, we have the integral from negative infinity to 0 of x times e to the negative x squared. Immediately we see the negative infinity as one of the limits of integration, and so for that reason this is an improper integral. We have an infinite limit of integration. Let's take a look at solving this. The first step is to replace the problematic limit with a variable name. So we have the integral, we'll just say from a to 0 of x e to the negative x squared dx. And now we're taking the limit as a approaches negative infinity. Now we try to solve this integral using fundamental theorem of calculus part 2. How do I solve that integral? Well, I notice an inner function here of negative x squared. The derivative of negative x squared is a negative 2x, which is a multiple of x. So I will use u substitution. I'm going to choose u to be the exponent on the exponential function. That's an inner function. The derivative of this inner function is negative 2x, and I can solve now for dx. dx equals du divided by negative 2x. Now, because I'm doing a definite integral, using u substitution, I must convert the limits of integration to be in terms of the new variable u. So I convert those limits now. I take the lower limit. If x equals a, u is negative x squared. So u would be negative a squared. And then take the upper limit. If x equals 0, that's the upper limit. Well, u is negative x squared, so negative 0 squared. U is still just 0. So I'll use those two expressions now for the new limits of integration. I'm integrating from negative a squared to 0. And the integral is x times e to the u, and dx becomes du divided by negative 2x. Now my x's can cancel. I have this negative 2 in the denominator. I want to bring that out as a negative 1/2. So I have negative 1/2 times the integral from negative a squared to 0 of e to the u du. The antiderivative of e to the u is simply e to the u. So negative 1/2 times e to the u, integrating from negative a squared to 0. We do not convert back in terms of x. Because I am using a definite integral, I leave everything in terms of the new variable. So now plug in the 0, plug in the negative a squared. I have the limit as a approaches negative infinity of negative 1/2 e to the 0 minus e to the negative a squared. E to the 0 is simply 1, and then I still have e to the negative a squared. Now I don't like this negative exponent here, so I'm going to rewrite this as 1 divided by e to the a squared. I'm also going to take out the negative 1/2 times 1 in front of the limit, and I have negative 1/2. Negative times negative here would be positive, so plus the limit as a goes to negative infinity of 1 divided by e to the positive a squared. All right, as a approaches negative infinity, the values in the exponent here are getting closer and closer to negative infinity squared. Because I'm squaring, this negative infinity doesn't actually matter. So I have larger and larger values in the denominator. When I'm dividing by larger and larger and larger values, the net result gets smaller and smaller. So this approaches 0. My answer here is negative 1/2. So I conclude that the integral converges to negative 1/2. Let's take a look at this one in Desmo. Here's the function x times e to the negative x squared. Looks like this. And we're finding the area from negative infinity to 0. That area is below the x-axis, so it is negative. And that area, although it is unbounded, has a value of negative 1/2. the integral converges. Let's take a look at problem 6. First of all, why do we have an improper integral here? What's the problem? There's no infinity as the limit of integration. The problem is the 0. So the reason that this is improper is because we have a discontinuity at x equals 0. Let's solve this integral. We start by replacing the problematic limit with a variable name. And we've already been using a and b, so let's be a little bit more imaginative. Let's just use the variable name c. So we have the integral from c to 1 divided by the square root of x, and I'll actually rewrite 1 over the square root of x as x to the negative 1/2 power. That will help me when I'm about to take the antiderivative. So 1 over square root of x can be written as x to the negative 1/2. Now we're taking the limit as c approaches 0 from the right-hand side. We have only positive values of x here. Okay, take antiderivatives. We add 1 to the power. So negative 1/2 plus 1, we have x to the positive 1/2. Divided by 1/2 is the same as multiplied by 2. So the antiderivative of x to the negative 1/2 is 2x to the 1/2. We have the limit as c approaches 0 from the right, and we're integrating from c to 1. Now, x to the 1/2 is the same as the square root of x. So I have the limit as c approaches 0 from the right, 2 square root of 1 minus 2 square root of c, plugging in the values for the limits of integration. This is what we get. 2 times square root of 1, that's just 2. So I have 2 minus the limit as c approaches 0 from the right of 2 square roots of c. Let's look at the square root function. Square root function looks something like this. If this is the c-axis, that is the square root of c. So as c approaches 0, square root of c also approaches a y value of 0. So this limit goes to 0. And our final answer here is simply 2. Finally, let's take a look at problem 7. Why is this integral improper? Well, there are actually 2 reasons. First of all, we can see the infinite limit of integration. So that's one reason. But also, notice that when x equals 0, the denominator is 0. So the whole thing would be undefined. We'd be dividing by 0. So we have a second reason that this integral is improper. We have a discontinuity at x equals 0. So we have 2 reasons why this is an improper integral. It's very improper. How do we solve this? Well, since we have a problem at both limits of integration, I need to split this integral into 2 separate integrals, each only having one problematic limit. So I could split at any value between 0 and infinity. I'll just split it up when x equals 1. So I write this as 2 integrals. The first one from 0 to 1. And the second integral is from 1 to infinity. I really have 2 improper integrals in one for this problem. So I set up 2 limits. I replace the 0 with an a, and then I take the limit as a approaches 0 from the right-hand side. There's my first limit. And then for the second improper integral, I replace the infinity with a b, take the limit as b approaches infinity. And we'll go from there. Now, in order to solve these integrals, we would have to find the antiderivative and then use fundamental theorem of calculus to plug in the a's and the b's and the 1's and get our answer. So since we have to do antiderivatives for the same exact integral, let's solve this separately. Let's just focus on the antiderivative of 1 divided by the square root of x times x plus 1. Once we find that antiderivative, we'll bring it back and use it in the problem. So we want to find the antiderivative of 1 divided by the square root of x times x plus 1. Let's think of the integration techniques that we know. We know integration by substitution, integration by parts, Trigonometric identities and partial fractions. There are no trig functions here, so we can't use trig identities. We might be tempted to try partial fractions because we see a fraction. But partial fractions works only when we have a rational function. We don't have a rational function here. I don't really see a way to do integration by parts, so I'm going to default to u substitution. But even then, I don't see a clear choice for u. This is a difficult integral. What do we do here? I would encourage you to take a minute, see if you can solve this. It's actually a very cool problem, and I'll show you the solution, but just see if you can work through this. Try to work through it using u substitution and see if you can solve it. All right, you can solve this using u substitution if you choose u to be the square root of x. All right, follow the steps. Take the derivative of the square root of x. It's 1 over 2 square roots of x. Solve for dx. We get dx equals 2 square root of x du. Now substitute into the integral. I have 1 over u times x plus 1 times dx, 2 square root of x du. This looks like a mess. I can't cancel x's here. The x plus 1, that can't cancel with square root of x. So we're left with u's and x's. We need the x's to go away, but they're not. So what do we do? This looks rather hopeless. Well, notice that the square root of x is u. So I'm going to replace the square root of x with u. That's my first step. And then the u's cancel. This is a problem. I wanted the x's to cancel, but the u's cancel. What in the world? I have 1 over x plus 1 du times 2 if we take this multiple of 2 out front. This is an issue. Can we salvage this? Can we solve this problem the rest of the way? Turns out that we can. Check this out. If I square both sides of this u equals the square root of x, I get u squared equals x. So this x is the same as u squared. I'm going to replace that x with u squared. Does this look familiar? I hope so. The antiderivative of 1 divided by u squared plus 1 is the arctangent. So this equals 2 times the arctangent of u. I replace the u with the square root of x, and I get the antiderivative that I was after. This is just a crazy u substitution problem. I hope you think it's as cool as I do. Let's go ahead and use this antiderivative in the integrals that we were dealing with. So for each of these integrals, the antiderivative is 2 times the arctangent of the square root of x. We'll plug in the a and plug in the 1, work through the fundamental theorem of calculus. We're still taking the limit here as a approaches 0 from the right. And for the second integral, I have the limit b approaches infinity. And I have again 2 arctangent of the square root of x from 1 to b. Okay, I plug in 1 to begin with. 2 arctangent square root of 1 is just 1, minus 2 times arctangent of the square root of a, plus the limit as b approaches infinity, 2 arctangent square root of b, minus 2 arctangent square root of 1, which is just 1. Take a look at this. I have plus 2 arctangent of 1 minus 2 arctangent of 1. I don't even need to know the value of arctangent of 1. Those cancel out. So I'm left with the limit as a approaches 0 from the right of negative 2 arctangent of a, so I'll just put a negative out front, arctangent of square root of a, plus the limit as b approaches infinity of 2 times the arctangent square root of b. All right, if a is approaching 0 from the right, then square root of a also approaches 0. So I could actually ignore this square root in here because the square root of a will be approaching 0. I'm just going to rewrite that just as a. This will help me analyze the limit just a little bit easier. So I'll just write a instead of the square root of a. And for the second limit, instead of having the square root of b, well, b goes to infinity. So if b is going to infinity, so does the square root of b. So I'm just going to replace this with a b. And now I'm thinking about limits of the arctangent function. I don't assume that we really are familiar with limits of the arctangent function, so let's take a look at Desmos and see if we can use the graph to intuitively solve these limits. Here is the graph of arctangent of x. Notice that as x approaches 0, the arctangent approaches 0 as well. So our first limit will be 0. As x goes to infinity, arctangent seems to have a horizontal asymptote. In fact, the asymptote is pi over 2. As x gets larger, the y values get closer to pi over 2. All right, so as b goes to infinity, arctangent of b goes to pi over 2, and as a goes to 0, arctangent of a also goes to 0. Let's use that for the limit values that we're working with. From the Desmos graph, this first limit is just 0. As a approaches 0, arctangent of a also approaches 0. So I have 0. The second limit is pi over 2. And since I have a 2 times the arctangent, my answer here is 2 times pi over 2. The final answer is simply pi. I think this is a great example. It's rather complicated, but this improper integral converges to the value of pi. Hey Siri, can you solve this integral for me?